thank you very much for joining us this afternoon at Caffe della Scienza. Today, January 27th, is also a highly symbolic date. Since 2000, in Italy we celebrate the date of memory, remembering January 27th, 1945, the date of the liberation of Auschwitz, quoted by Primo Levi in his book The Truth. Today we join in the commemoration and the memory of the victims of the Shoah. To never forget, we hope science can contribute to a better world. I would like to thank our Consul General for promoting Caffe della Scienza and the Consulate staff for their invaluable help, support and enthusiasm in organizing this event. Today we have two speakers, two astrophysicists, who will tell us in a synergistic talk how planetary systems are formed and how scientific knowledge of the systems has been revolutionized by the new generation of telescopes. The first speaker is Professor Isella from the Department of Physics and Astronomy at the Rice University, and the second one is Professor Banzatti from the Department of Physics of Texas State University in San Marcos. So I give the floor to Professor Isella. Thank you.
Well, thank you everybody for coming first place. I would like to introduce a little bit myself and maybe Andrea then will do the same. So how we got here. I did all my study in Italy. So I got my laurea in astronomy from Padova long time ago. And then I did my PhD in physics and astrophysics in Milano, at the University Statale in Milano. And at that time in Italy was this, I don't know if still the same system, I hope not, but there was this weird system where you can get a PhD position without the money, right? So, I was admitted at Milano with this position as a graduate student, but there were no money for actually pay my salary, right? So very fortunately, in Florence, in Firenze, at the Osservatorio di Arcetri, there was a very large group of astrophysicists studying the formation of stars and planets. At that time, it was mostly stars. They were looking for someone that could do some project that was very similar to what I did in my thesis. And so I ended up being paid by Firenze, by the INAF, the Istituto Nazionale di Astrofisica. And so, I had an official position in Milano and was commuting up and down. I'm originally from the province of Milano, so, but I spent most of my time in Firenze as a graduate student. During my PhD in Firenze, I had collaboration with the United States, particularly a group working on millimeter observation, something I'm going to talk about today. This was a group in Caltech in California. So when I finished my PhD, I applied for a NASA postdoctoral fellowship. So I got a NASA postdoctoral fellowship, so I moved to California and to work at Caltech. I was working on something that NASA was doing at that time, was building optical interferometers and radio interferometers, and I'm going to tell you what interferometers are. And then I stayed at Caltech for 7 years, and then I started applying for faculty position in the US. And at that time, there were not many jobs in Italy. The only things that Italy could offer were kind of temporary position in the university. Say, well, then I stay in the US. What's the point? And I got a job here at Rice as an assistant professor in 2014, and then I got promoted to associate professor a couple of years ago. So, that's the long trip that brought me from a little town in provincial Milan, the Monza, to Houston, essentially. And I think Andrea has similar experience. Andrea, do you want to introduce yourself, say something about you?
Yeah. Yes, can you hear me?
Yes, we can hear you, and let's see if I can see on my laptop.
Yeah, so You know, I have one slide that I usually show to my students to introduce myself. So if you like, I can show that one.
Yeah, sure.
I think, can you see the slide?
Yes.
All right, so I put together the, sorry.
Go ahead.
So I put together this slide to tell my American students where I'm from. So I sometimes I even have to tell them where Italy is. That's why I have a map and I zoom on Italy here. And so I'm from Milano. So I usually show with pride our symbols of the city, the Duomo, the Castello, and the trams, which is very unusual for Americans. So they always ask me what that is. And let me see. Yeah, so then I moved to Munich for my PhD. And then I moved to Munich for thesis with actually a close collaborator of Andrea. And at that time, we even wrote a paper together. I was a young student and we never even met each other at the time. Then I moved to Zurich, to the ETH in Zurich, the Swiss Federal Institute of Technology, with an American professor. And that's why I ended up on this side of the ocean later, after my PhD for a first research assignment in Baltimore, Maryland. At that time, I was working at the Space Telescope Science Institute, which is one of the leading NASA institutes that manages the space telescopes, the Hubble Space Telescope and the James Webb Space Telescope. Then I decided that was not enough, so I moved across the country with my family. At that time, we had one kid moving here, and then we had another kid moving there, and we ended up in Tucson, Arizona, almost. And Tucson in Arizona in general is another fantastic place for astronomical observations. It's a very dry place, desert. So astronomers typically like to live where other human beings don't like to live. And so deserts. And so, yeah, so I was in Tucson for another 3 years. And then we landed in Austin, in Texas in 2019. So this is the 4th year that I and my family are in Austin. And in between going across the US, I visited the best places for astronomical observations on Earth, and not in space, not yet. I haven't been in space yet, but I've been on the best places on Earth. One is Hawaii. And again, even from here, from the map, you see that astronomers don't like people. They like to be very far away from civilization, so in the middle of the ocean. And the second, the place for the best optical and infrared astronomy is in Chile. And even here from the map, you see that it's a desert in the middle of a green country. So even there, it's actually where the telescope that even Andrea Isella uses, ALMA, and he will show you more about that. It's an amazing place. When you're there, it looks like being on Mars. So extreme of a desert it is. And yeah, so this is my story.
Thank you, Andrea. Yeah, so you see astronomers move around a lot. I think it's pretty common for, there are in Italy there are many astronomers that studied in Italy and did everything in Italy, but nowadays it's much more common to really move around and maybe go back to Italy. I have to say that in the recent year, thanks to the European Research Council, I think the situation in Europe in general and in Italy improved a lot compared to when I moved to the US. There's much more money provided by Europe. And so a lot of people are going back, I have to say, which is pretty good. But okay, moving on. So today we are going to tell you something about how planets form. So I'm going to try to motivate a little bit why you want to understand how planetary systems form. And particularly we live in a very interesting time where we have new telescopes that are changing drastically the way we understand the formation of planets. And some of the research I'm going to show you is sponsored by some of the institutions up there, including National Science Foundation, NASA, and in Texas also we have the Welch Foundation, which is a very, it's a foundation that is a private foundation that supports research in fundamental chemistry. I'm not going to talk about chemistry today, but some of the things I do are related to chemistry. Okay, so let me start from something we know relatively well, which is the solar system. We have been studying the solar system for centuries, and for the last 100 years or 50 years, we have been able to send probes and land probes on Mars and send probes to Jupiter, Saturn, and all the other planets, including Pluto, and also Venus and Mercury. And the exploration of the solar system is really motivated by one fundamental question, which is how did our planet form and how the solar system formed? And we want to know if there is life elsewhere in the solar system. We want to know if there are habitable environment elsewhere in the solar system. So we send we have this robot on Mars that look for signature of life. We are planning to send robots on Jupiter moons to search for life. And so the fundamental question is really how we form, right? When you look at the solar system a little bit in detail, something that might strike you is that there are 8 major planets, right? Pluto is not the planet anymore, so forget Pluto. There are 8 major planets, and they're very different, right? So you go from Mercury, which is a rock close to the sun, to a beautiful planet like Earth. Then there is Venus, which is next to the Earth, but is nasty because it has all this poisonous atmosphere. And you can ask yourself, how is that possible that 2 planets so close are so different? Mars is a little one, much smaller than Earth, doesn't have a very thin atmosphere. It's colder than Earth, so it's not very good for life. And then you move out in the outer solar system and completely different story there. The outer solar system, you have this, what we call the gas giant. Jupiter is the biggest one. It's 300 times bigger, more massive than Earth. So it takes 300 Earth to make a Jupiter. And these are very thick, very massive planets with a lot of gas, mostly made of hydrogen. And we still don't know many things. So for example, we cannot really look inside this giant planet. We think there is a core, a rocky core inside for example, Jupiter, which is maybe 20, 30 times the mass of Earth. But, how do you get all this diversity in one single system? Why there are planets so different? Why there are this very clear architecture between inner planetary system and outer planetary system? Is that common, right? Is that common everywhere? So this kind of question motivate the exploration of the solar system and why we want to study how the solar system forms. But the solar system is not the only planetary system in the universe, right? So in the last 20 years, we discovered many, many planets outside the solar system. So this figure, and there is an animation, apologize for the scale, which is a bit technical, but this is perhaps the most technical picture I have. So on this horizontal axis, there is the distance of a planet from the star. Right? This is expressing astronomical units. The astronomical unit is the mean distance between the Earth and the Sun, which is 150 million kilometers. Right? And this is log scale. The point is this is 1, this is 10, 100, 1,000. So, and on the vertical axis, there is the mass of the planet expressed in units of the Earth mass. So Earth is at 1, 1. Okay. So Earth is there. This is Mercury. Mercury is about 0.4 astronomical unit. It's much lighter than Earth. Jupiter is out there, 5 astronomical unit, 300 times the mass of the Earth. Okay. So starting in 1888, there was the first discovery of a planet around a weird star. And then started in 1991, 1995. Thanks to new instrumentation, we discovered many, many planets. So each dot here is a planet around the star that is not the sun. And when I made this slide 4 years ago, 3-4 years ago, so I apologize for that, only goes up to 2019. But if you check today, there are probably something like 5,000 what we call exoplanets, so planets outside the solar system. And this field really exploded, and there was a Nobel Prize awarded in 2018 to these two guys, that Didier Queloz and Michel Mayor, that were those that discovered the first planet outside the solar system, called 51 Pegasus. They received Nobel Prize in 2019. Okay, so we went from a situation where we only had the solar system as an example of planetary system to a situation where now we have thousands of planetary systems. And if the solar system has planets that are different, when you look at other planetary systems, things become even more complicated. So as I said, on this axis there is the mass of the planets, right? So each dot is a new discovery. There are no dots down here, not because these planets don't exist, but because these planets are very, very difficult to detect and discover. Right? So we cannot observe planets if they are down here. As you can see, there are not many dots close to Earth, meaning that despite the fact we have discovered thousands of exoplanets, we still didn't find a planet that is like Earth. Okay? We tend to find planets that are much bigger than Earth and much closer to the star because these are easy to detect and discover. And this point tend to cluster. There are three groups. There is a group down here, a group up there. And these two groups, as you can see, there are no planets of the solar system in these two groups. So before this observation, we didn't know that this planet exists at all. And these are weird planets. Okay. So the group up there, these are called hot Jupiters. These are planets that are big as Jupiter, but they are very, very close. They graze their own star as they orbit. They are very, very close to the star, much closer than Mercury. Right? So it's like you take Jupiter, you bring it in very close to the sun. Now the planet becomes very hot because it's close to its own star. And so it's very weird environment that nobody ever predicted that these planets existed before they were discovered. Another group of planets that we don't have in the solar system are these planets here, which are a little bigger than Earth, 5 to 10 times bigger than Earth, and closer in. Right? So, and again, we don't have anything like that in the solar system. And then the group over there, which is partially covered, these are more like the regular, the one around Jupiter. These are more like the regular Jupiters. Okay. And again, as I said, there are for sure planets down here, but these are very difficult to observe. Okay, so now you don't only, the idea is that we need to explain the formation of the solar system. We also want to understand how all these other planetary systems come to be. And if you ask yourself, okay, so we discover 5,000 exoplanetary systems, are they like our own solar system or are they very different? Most of them are very different. And indeed, most of the planets that we have discovered, we don't have any example of this planet in the solar system. So these figures show, it's an histogram that show this is the planet size in Earth sizes. So Earth is here. These are planets that are much bigger, 8 times bigger in size, up to 20 times bigger. And the most common planets in the universe are actually in these two beings, which are called super Earth, because they are between 2 and 3 times bigger than Earth in radius. And for some reason, we don't have anything like that in the solar system. So the solar system might, for what we know, it might be weird, because it doesn't have the most common planet in the universe that we can see. Okay? And actually, this is the average number of planets per star. So something that was really a big discovery is that if you ask yourself, so if you pick a random star in the universe, what's the probability that that star will have a planet? Well, actually, these new discoveries show that, in average, there are planets around every star in the universe. So in our galaxy, we have 100 billion stars. Well, so there are at least 100 billion planets only in our galaxy. So, and in average, right, every 3 stars, you should find something like Earth. This kind of planets. Planets like Jupiter are more rare, so to find. Okay, so this should give you kind of a general picture and put the solar system in the context of all this discovery. So right now, some of the exoplanets that have been discovered are really weird. I show you two very extreme cases. On the left is called Kepler-11. Kepler-11, so this is the solar system. And Kepler-11 has 1, 2, 3, 4, 5 planets orbiting so close to the star that are all packed within the orbit of Mercury. Okay, this is Mercury. We generally think Mercury is very close to the sun. Now you have this solar system where you have 5 planets bigger than Earth orbiting inside the orbit of Mercury. And so how do you get such a compact system? On the other extreme, there are objects like this one is called HR 8799. So what this video shows, there is a star at the center that has been, the light has been removed because the star light is much, much brighter than the planet. So if you show the star, you're not going to see the planet. So the star has been removed. And these white dots you see are planets orbiting around the star. And now this is extreme because in that case you have 4 planets. The smallest one is probably 5 times bigger than Jupiter, and they are very far away. The closer in is 20 astronomical units. 20 astronomical units. Jupiter was 5 astronomical units away from the sun. Okay, 20 is like Pluto. Farther out than Pluto, the farther out is very far away. So how in the world you come up with so much diversity? Okay, first of all, planets are common in the universe. Every star in the universe has planets, for what we understand. They're all very diverse, okay? So this motivates what I do, which is try to understand how planetary systems form, why they are so diverse, and maybe what make a planet habitable and other planet not habitable, okay? So I'm gonna show you, I'm not gonna keep you here for hours telling you all I do, so I'm gonna focus only on one very specific aspect. Okay, so how do planetary systems form? And so the general picture is relatively easy to understand. In the universe, there are clouds of gas that we call molecular clouds. They are cold, they are made of molecules. And they can decide to collapse. Gravity attracts things together, so this cloud collapses. If there is a little bit of rotation, and if you in physics class, you know that when you collapse something, there is things called conservation of angular momentum. So as things collapse, the angular momentum is conserved, which means things must spin up. So they start to rotate faster. And instead of everything collapsing in a single object, which would be a star, you form what we call a protostar, surrounded by a disk of material that rotates, right? So now this happens, from point 1 to point 2 takes maybe 1 million years or less, right? Which is very short compared, the solar system is 4.5 billion years old. So it's a very, very short time scale. And then what we think is that in this disk, so the magic happened, the planet formed. How they form, we don't know. And then after a while, after a few million years, the material either ends up on the planet or ends up on the star or gets dispersed away. And after about 10, 20 million years, you are left with something that looks like the solar system or a star with planets and nothing else. And so we don't know how planets form. So we don't know what happens in this phase such that the planet, so this material comes together and forms planets. And that's what I study and what Andrea studies. So what tool do we have to do this kind of study? Okay, there are two main tools. One is we can take pictures of this baby planetary system as they form. So the solar system is old, it's 4.5 billion years old. We can study the solar system and trying to reconstruct the history of the solar system. Or the approach I take is that we go and look at the planetary systems that are forming nowadays and try to understand what we see. So imaging, that's what I'm going to talk about. Or you can do spectroscopy. If you cannot take pictures because these objects are very small, we can still do a lot of things. And Andrea Banzatti will focus on the spectroscopy aspect of things and all the cool things that he's doing with JWST. Okay, so I told you planetary systems are forming nowadays. Okay, it takes million years, but they are still forming in the galaxy. And so where do you go to search for planetary systems that are forming? You go and you look in the region close to the sun where there is what we call stellar and planetary nurseries, where this gas is coming together and forming stars. This is called star forming region. This is a beautiful star picture of the Orion Nebula. If you are an amateur astronomer, I don't know, but Orion is a famous constellation, visible in the winter. If you go out, well, tonight it's cloudy. Yesterday it was up in the sky from Houston in the winter. And in the middle of the constellation, there is this beautiful molecular cloud called the Orion Nebula Cluster. This was an image taken with the Hubble Space Telescope. And there are a lot of things going on here. But if you zoom in, what you see are objects like this one. And what this is your baby planetary system. So the white dot at the center is a newborn star. And the dark ring around is this material that forms a disk. And then you have this kind of cocoon that looks like a tadpole that is illuminated by bright star, and a lot of things are going on. But this is a baby planetary system, which is only maybe 1 million years old. Okay? So very, very young in astronomical scale. So if you want to understand how planets form, this is by reference, just to give you the scale, 3,000 astronomical units. So now you have to zoom in. You need a telescope that is so powerful that can zoom in and really give you a high definition picture of what's going on at the center. And that's really difficult because these objects are very, very small. So this baby planetary system, if you put them in the sky, the closest to us are 2,000, 3,000 times smaller than the full moon. Okay, so, and you want to take pictures, so you need some device that allows you to look at the sky, and they are also dim. They are not only small, they are very faint. So it's been a challenge to observe this object for many, many decades until recently, where we have huge progresses in instrumentation. So Andrea Banzatti mentioned Chile, the Atacama Desert. In the Atacama Desert, we have a fantastic telescope. It's called the Atacama Large Millimeter Array. It's a weird telescope. If you know anything of telescope, you look at this guy and say, what the heck is this? So this is a radio telescope. It's made of radio antennas. There are 64 radio antennas. Each of these guys is 12 meters in size, just to give you an idea. Right? This is a track. See how big the scale. Right? So these are huge antennas. There are 64 of them. It's located at 5,000 meters above the sea level, and you want to go very high because the atmosphere is an opaque screen, so you want to get rid of as much atmosphere you want, you can. And it's so this is a 5,000 meter in one of the driest place in Earth. Although, as you can see from the mountain, there is snow. So in the winter, in the southern winter, it can snow. And somehow, since they put the telescope, it's not a lot. Never snowed before, and then they put the telescope and starts snowing. Anyway. So what you can do with this powerful telescope is that these objects are very small, right? And in order to take picture of very small objects, generally you need very large telescopes. But there is a limit, right? We cannot build a telescope that is 10 kilometers in diameter. It's impossible. So we can build telescopes that are maybe 10 meters or 20 meters or even 100 meters in diameter, but not kilometers. So the workaround we use in astronomy is that we build a lot of telescopes. Now we combine them together using this technique called interferometry. And the result is like having a telescope which is as big as the distance between antennas. So now you can build many antennas, you can spread them out, and that's why you pick a region that is flat. And ALMA, when you can move them, you can load them on trucks and move them around. There is this huge track that lifts the antenna, move around, and then you can space them 16 kilometers apart. And when you combine the light, it's like having a telescope of 16 kilometers in diameter, which is fantastic. So this telescope has been around since 2011. When I was at Caltech, I was working on a much smaller telescope, kind of a precursor of this one. It was called Karma in California. And I was taking images of this baby planetary system with these precursors telescope. By the way, ALMA can take a picture of a center 5 miles away, give you the resolution, the capability of taking pictures. That's what we need to observe this baby planetary system. Okay, so I was in California. When I moved to Caltech, I was working on this new telescope at the time. It was 2007. That used, we had 16 antennas, much smaller than ALMA. Instead of being 5,000 meter elevation, we were at 2,000 meter elevation. And we were trying to take a picture of this baby planetary system. This is one of my preferred friends. Here, my friend is a star called NWC 758. It's not very important. The point is that it's one of these baby planetary systems. You want to take a picture, you want to see what's going on. And that's a picture we took. Right? And you say, well, what? It's not very, what is that? 2 blobs of light. And the scale here, stand astronomy. So even these pictures are not really impressive at all. We were able to do science and measure things. Right? We want to measure how much material you have around the star, how the material is spread out, these disks, how it moves, and things like that. So then ALMA came around in 2011, and when I was able to use the telescope, I said, well, now I want to go back and look at this guy. The same object, same observation with this new telescope, right? And then suddenly say, oh, now I see things, right? So this was before, and this was after, right? So, and so these images show many more details. So let me tell you a little bit what's going on here. So this object is one of these younger systems that perhaps is forming planet. We think it's forming planet. If you put the solar system, just to give you a scale, you put the solar system on top, that's the size of the solar system. So what this image shows, so black means that there is nothing, you don't see any light. And white means you measure light at wavelength. These telescopes work at millimeter wavelength. These are the same wavelength that your microwave always used to warm up your dinner or your milk. And this emission comes from tiny dust particles, like sand. So the idea is that there is a star, and when these systems are young, this material is made of gas, and Banzatti will talk about gas, and there is a lot of dust particles, right? And we want to understand what these dust particles do, because we live on a big dust particle, which is Earth, right? It's a big rock, right? The idea, if you could zoom in, the idea is that these dust particles in this disk that are very small, they have a size which is 1 millionth of a meter, right? 1 micron. Somehow they come together, they stick together, they collide, they stick, they grow in size, at the point that you form what we call planetary embryos. So planetary embryos are objects like the moon. Okay, the idea is that you stick together a lot of small particles, you grow things like the moon, and then this object can collide and grow and give you things like Earth. Right? That's the general idea, what theory tells us, right? But we never had any observation to really test this theory, except what we have from the solar system. So this new, I'm not going to go in any detail here, but the point is that by taking this observation, we can measure how much, what's the amount of dust in different positions, how it moves, what are the chemical properties of this dust, and how this process of coagulation from dust to planet happens, okay? So we were not able to do this in the past. So, okay, so now, since 2011, we have this new fantastic telescope. And obviously, you don't want to stop at one baby planetary system. You want to observe many baby planetary systems. And so, together with collaborators, we did pick 20 objects that we already observed with previous telescope, but with these very crappy images where you see blobs. And we started looking at them with ALMA. And this picture is a family portrait of these 20 objects. And these are all pictures. Don't look at the color. The color don't mean anything. These are all kind of grayscale images. The point is that the brighter it is the image, the more emission you have, the more dust particles you see. And all the emission you see here is from these sand particles that orbit around the star. And one of the really big discovery that we really were not expecting is that you have all these kind of rings, right? Like annuli. And you may ask yourself, why do you have these kind of annular gaps where you have this dark, mean there is nothing, and then you have a big annulus of dust and an annulus of dust here? And the question is, what's going on here? So if you know something about the solar system, you know that Saturn has rings. And if you look at Saturn rings are made of tiny particles. And when you look at Saturn rings, you see that there are these gaps in the rings, right? And they say, well, why there are gaps in the rings? Because these gaps look like these dark gaps we have here. Now, these are much bigger systems. We have a star surrounded by a disk of dust. Right? Saturn is a planet surrounded by a disk of dust. So it's a bit different, but these gaps look similar to the other gaps. And so you can ask yourself, okay, why there are gaps in Saturn rings? And if you zoom in, you see that there are gaps in Saturn rings because in the Saturn rings, there are these asteroids, what are called shepherd moons, right? So you have a moon, and what the moon does, pushes away material and opens up a gap in Saturn rings. Okay? So the physics is exactly the same. The idea is that instead of having moons, what we have is planets that are forming, and as they form and they become massive, they push away the material and they create gaps. Right? Now, this planet, we don't see the planet. We see this feature, we don't see the planets yet. Except in one case, I'm going to show you that case. But the idea is that somewhere in this dark region, there are planets over there that we might be able to discover very soon with the new space telescope, which is the James Webb Space Telescope. And we have observation scheduled, so they are in the, you have to submit a proposal, it must be accepted, they create a queue, and then you have to wait your turn, and then they will do the observation, and then, so by the time you say, oh, I would like to observe this with JWST, at the time you actually get the observation, is at, 3 years pass or 4, it's a very, it takes some time. It's getting better, but in the past with delays. The point is that this coming summer, we are observing this object with JWST to look for planets in these gaps. So maybe you will hear soon that we discover planets. Okay, there is only one case where you actually see the planet. So this is, again, one of my other friends. It's called PDS 70. It's not important. It's a star that is very, very similar to the Sun. It's almost a twin of the Sun, but it's much, much younger. Again, a few million years old. The star is at the center of these images. These are two images. Look at this one. So the star is here and it is being removed. The white stuff are two planets, bigger than Jupiter, very young. They are still growing. They are still accreting material and growing. And the brown stuff are these dust particles that orbit around the star, right? So this scale is 20 astronomical units. And you can fit the entire solar system in this dark inner region. This is the only system where we detected planets and the disk, and so we can very well study the interaction between the planet and the material. And if you squeeze your eyes and you zoom in, so that's the planet that we see with ALMA. And but in this millimeter wave, you actually don't see the planet. The planets are way too thin. So this actually blob of light is not the planet itself. But what happens is that there is a planet that is forming, and there is a disk around the planet. So if you think about Jupiter, there are the Galilean moons, right, discovered by Galileo, Io, Europa, Ganymede, Callisto, big four moons. the moons around Jupiter, we believe, formed in a disk around Jupiter when Jupiter was young. We call this circumplanetary disk. So what we see here is the evidence that there is a planet, and the planet is surrounded by a disk, a circumplanetary disk. And this was really the first discovery ever of a circumplanetary disk, and it was picked up also by CNN. We never saw circumplanetary disk before. So that was very exciting. Okay, I'm at the end of my talk, which went longer than 20 minutes. So what is the conclusion? So we are observing this baby planetary system, and the question again is, how do planets form? And the revolution is that we have this new beautiful observation. And they are telling a story that is very different from what we had in mind before this observation was done. So I'm going to conclude showing this picture. So this picture is similar to the previous one, but a bit different. So now this is age in billions of years. So the sun, the solar system is 4.5 billion years. So it's here. And these are all the planets we have discovered. And this is the distance from the star, okay, in astronomical units. So Earth is 1, Jupiter is 5. And these are all the planets around all the stars, right? And you have, the Jupiter, the super Earth, or more like the Jupiter. So this new observation we are obtaining are giving us the planet in the red circle. Right? And as you can see, okay, we cannot see planet down here. So we don't know how many planets we have down here. We cannot see them. Right? We don't have telescope that are powerful enough. But as you can see, there is kind of a mismatch between this and this because there are not many planets up there, right? And there are much fewer objects. So these planets are here were really not predicted, right? So these are planets that form very, very far away from their star. And before we did this observation, the idea is that all the planets form very close to the star, right? All the planets typically tend to form here around 1 AU. And if you see them very far away, it's because they form here and they move out, right? Because theoreticians couldn't find any way to form planets so far from the star, right? Because generally there is not enough material at 100 astronomical units to form planets. There is just nothing there. But what we are finding is that actually planet finds a way, somehow nature finds a way to form planets so far away from the star. Right? It's really new and it's not explained. So I think it's exciting that every time we have new telescope, we discover things that goes against our previous ideas, and that's how you make discovery and you move on. Okay. So this is one of the things. So this is what I do mostly in my time. I do other things that I don't have time to talk about. But with that, I would like to stop here because I went already probably half an hour. And it's up to you. If you have questions, maybe we can take one or two, or we can give the floor to Andrea Banzatti, and then we can have questions at the end. So as you like.
Can I have a question?
Sure.
Why don't, maybe I missed it before. Did you discuss the difference between the sun and the other stars, the other suns, call it?
Yes.
Which are, I think, the engine of all this, right? You don't have a star, you don't have planets, or at least.
Sure, there are stars.
So wouldn't it be useful to compare different stars, say different suns, and see what they differ rather than the product?
Yeah, no, and we have done that. Yes, there is a huge amount of work done. So people have, if you take, as I said, there are about 5,000 exoplanetary systems, and you can group them based on the properties of the star. We can measure stellar properties pretty well. So we can tell if a star is like the sun or is different from the sun. We can measure them.
Differ? How do they differ?
The stars?
Yeah.
So stars differ essentially by the mass. There are stars that are more mass. Composition is another aspect, but the mass is the main parameter. The star rotates. Yes, there are stars. Well, there are stars that rotate faster than the sun and slower than the sun, but that's not really relevant. Really, what matters is the mass, because the mass sets the temperature and sets how much energy a star emits. Right? And indeed, people, if you group planets based on their star, you find differences. You find that if the stars that are bigger tend to have bigger planets. The stars that are smaller in mass tend to have smaller planets. And it goes back to the idea of disks, right? Because how do you get a bigger star? You need more material to fall into. You need to start with more material in the first place. And if you have more material, you end up with a bigger star, but also with bigger planets, because you have more material to form planets. Right? So there is a lot of research done in that field. There are many dimensions, right? So you can look at stars, you can look at planets in different regions of the sky. If maybe there is some environmental effect, right? Planet from in one region might be different from planet from another regions. There are many different variables that one can explore. Yes.
Excuse my ignorance. But when I look at the night sky and I see all the stars, does each one of the stars have a planetary system around it?
In average, yes. That's what the new discoveries tell us. That in average, every star in the universe has at least one planet. Probably more.
Wow.
Yes, it's kind of mind-blowing, right?
Yes, totally.
Yes.
I'll look at it differently.
Yes.
You ever witnessed a solar system can have a star?
Yes. There are systems around so it's more difficult because when you have two stars, well, there are different configurations. You can have two stars and planet goes only around one. Or you can have planets that go around binary system. There are, yes, have been discovered. They are rare because they are more unstable, right? So just not stable orbit. But yes, there are planets around circumbinary, what we call circumbinary planets. Yes, but think about Jupiter as a star, right? You can have the moons of Jupiter going around Jupiter. So you can have a configuration where you have two stars and the planet only orbit around one star, and that's perfectly fine. Or you can have a situation where you have two stars and planets that orbit around both. Okay. No, they describe an orbit which is circular or elliptical around both stars if they are far away. Yeah, there are many weird even. I don't know if we have found planets around triple system, but okay, we should probably move on to Andrea. Sure.
Yeah, just a quick question. Yeah, I like your slide. It showed the difference between the low resolution, high resolution, maybe planetary system. I was wondering, how do you know with the low resolution image that it's really maybe planetary system and it's not something?
Yeah, there are many other diagnostic, right? Well, actually, Andrea is going to talk about that. Okay. You can observe this planet in different wavelength, and when you combine everything together, there is a huge amount of diagnostic you can. So I'm only talking about one because there's no time to go in detail on others. But there are many other information. These are not the only information. Do you want to share?
Yes. Okay. So yeah, again, thank you all, and thank you, Anta, for organizing this. It's really it's an honor. I would have liked to be there in person. My wife was there this morning. Unfortunately, I couldn't join because of actually deadlines and work to do today. James Webb Space Telescope that I will talk about in the talk, and yeah, but it's really a pleasure to share a story with Andrea Isella. Again, it's quite, I have two Andreas so close to each other working on the same topic and at the same time on very complementary aspects of the topic, as you will see. So it's yeah, it's really a unique story. It's good to be here in Texas together and to be now connected with you there. So yeah, after the images that Andrea showed, I think I have to break a wall here about spectroscopy and tell you why we do that and what it is. First of all, I get students who have a hard time pronouncing the word. They sometimes they cannot say spectro what, and so. Spectroscopy is a fundamental technique in astronomy, as I will show, but it's usually not as beautiful as images or as immediate as an image to speak to people. That's why the general audience usually knows images from the Hubble Space Telescope, now from James Webb, And usually, no, the public likes to see colorful images. So in fact, spectra too are very colorful, and we can make pretty images too with spectra. Although again, the beauty of spectra is a little more hidden. So here you see two examples. One that I made with myself, just with a piece of glass on my desk in my office in Tucson. So if you put a piece of glass and let sunlight go through it, you see dispersion, the dispersion of light that makes a rainbow. That's the same principle that happens when you see a rainbow when it's raining and there is the sun. This same effect that you see here happens in each droplet of water, believe it or not. It's amazing how nature works. And each droplet is dispersing the colors of white light such that making those beautiful rainbow in the sky. Now, in the background here, you see another beautiful image that is actually a bit edited afterwards. So it's a composite of a spectra of our own sun, very high resolution spectrum. This is the same sun, is in Tucson. It's done with one of the best telescopes they have right there. And again, it's a composite where you see the same colors that you see here, but here they are very compact, and here you see them very spread and so spread out and seen in such a high quality that you can distinguish all these dark lines. Have you ever heard, anybody has ever heard that our sun has dark lines in its spectrum? Can you raise your hand to you?
A few.
So these dark lines that you see in this spectrum contain an amazing amount of information about the chemistry, physics of the surface of the sun. And this is how we learn about what's happening on the surface of the sun and the chemistry and the chemical elements that are there. So let me share a quote, spectroscopy, to tell you how important it is in astronomy. Here is it. It is, there have been 3 significant milestones in the history of observational astronomy: the invention of the telescope, photography, and the spectroscope. The spectroscope has contributed more to the science than any other telescope accessory. It has been said that 85% of all astronomical discoveries have been made with the spectroscope. So trying to, I don't know if Andrea, how no, if you're I
agree.
You agree? Perfect. But it's and I will show some. I will show examples of that. So I'll not leave it at the quote. So spectroscopy is essentially, again, the dispersion of colors that are in light, the light that we see as white light with our eyes. This goes back to Newton. Newton was the first to use prisms, in glass prisms, to disperse them and study, made a theory of light and color. Newton was the first. And then after these initial discoveries, a long time passed until the history of spectroscopy joins the history and the birth of modern astrophysics. And we as Italians should be very proud of that, because in fact, one of the earliest pioneers in spectroscopy is an Italian. So a development of the spectroscope as connected to telescopes made really, again, determine the birth of what we call modern astrophysics. Why is it astrophysics? Because we started to study the chemistry and the physics of the universe. So here you see the telescope. I don't know if you knew that, but there was a Jesuit priest in Rome, Father Angelo Secchi, and here you see an illustration of his telescope. And what's most amusing is that that telescope was placed on the top of a church. You see here was the St. Ignatius Church in Rome. It's now dismantled, but you can still visit. I checked on YouTube. I see that there are guided tours. You can go at the top of this church and still see the basement of that dome. But now, can you believe it? Now, if you go to Rome and you see one church that has an additional dome on top of it, that is not the dome of the church, but is the dome of the telescope. That was quite a thing to see. And so Father Secchi was one of the very few earliest who took thousands thousands of spectra by hand of stars. And here you see an illustration of the earliest stellar spectra that he took. So you see that very early, as soon as the technique was available and using it, they realized that stellar spectra, these are spectra from 4 different stars, they realized that they looked very different. And they were trying to understand why. And later, it took some time. By the early 1900s, they understood that each line here in the spectrum was a unique imprint from a chemical element, and that therefore, what we are studying when we observe spectra is the chemistry of the universe. And there was a huge discovery at the time that again opened up the modern astrophysics and the study of stellar spectroscopy and spectra from all other environments in space that we can observe today. So, what big discoveries that have been done with spectroscopy? Again, I told you that I would not leave it at that quote, but I would tell you what these are, a limited list. Oops. Okay. So, first of all, what I just said, the stars are made of chemical elements found on Earth. And this was work by Fraunhofer, Kirchhoff, and Bunsen, Huygens, and Secchi in 1909. Then the expansion of the universe. This was a discovery made spectroscopy by Edwin Hubble in the US in 1929. The spiral structure of our galaxy. As you know, if you look in the, now if you've ever seen our own galaxy in a night sky, if you go in a very good spot, you can see our galaxy, the shape of our galaxy in the sky. And how does it look like? It doesn't look like a spiral because we are in it, no? So it looks like a disk. No, you look, it's a stripe of stars and clouds and dark clouds as a stripe on the sky. Now, by being in the disk of the galaxy, we don't know the shape of our galaxy. But with spectroscopy, instead, it was possible to see from the velocity of stars in different directions that it's actually a spiral galaxy, just like other stars, like the Andromeda galaxies that we see near to us. Dark matter is a discovery from spectroscopy, from the flat rotation curve of other galaxies. And last but not least, exoplanets that already Andrea showed. This deserves some particular attention here in this list of discoveries from spectroscopy, because it was finally, I would say, awarded the Nobel Prize in Physics in 2019, just when I started at Texas State. I remember I was in my office when I saw that news, and I ran out of my office screaming, no, not exactly, but just very excited, and telling all my colleagues, finally, they gave the Nobel Prize the discoverers of the first exoplanet around the solar mass star. So you see Michel Mayor and Didier Queloz, 2 Swiss astronomers. I told you that I did my PhD in Zurich in Switzerland, and I had to meet twice with Didier Queloz and have a good glass of Swiss wine together and dinner when I asked him to tell me about his discovery. It's really an amazing story. You find a YouTube video on that. I suggest you to go and check it out. It's fantastic. You seeing Didier explaining that discovery. He was a PhD student when he made the discovery. So you see, a Nobel Prize for something that you do during your PhD. Not bad. So this discovery was made. You see this. This is the signal that tells us that the star that they were observing kept moving away from us and towards us, away from us and towards us. And it's worth going one step more into the details to see that, because I'm sure you can capture the basics of this technique. And I show here a romantic view, simplified view. But if you take one of these spectra, with thousands of these dark lines, and you keep monitoring and taking spectrum of the spectrum, and you look at those dark lines, you will see that those dark lines are moving. Now, so you see this white line, vertical line is reference. Okay, this is the reference. This is where those lines, and then you see at time 1 that those lines are shifted to one side of it, and time 2 they are shifted to the other side. And then you keep observing and observing, and you see that these lines keep doing this and this. So the position of these tell us about the velocity of the star. And the star, as you see in this cartoon, is moving away and towards us, away and towards us, away and towards us. At that time, they were asking themselves, what the heck can produce such an effect if it is noise? And they worked a lot to determine that it was actually not the noise of the instrument. And finally, when they were convinced that it was actually a real signal, they realized that it was a Jupiter mass planet that was orbiting extremely close to its own star. And by gravitational pull, it had to be a massive planet. So it was a Jupiter-sized planet. By gravitational pull, even the star felt the gravity of the planet. And so even the star is not only the planet that is orbiting, but actually the star plus planet system is orbiting around the common center of mass. So even the star is moving a little bit. But if you do very high precision spectroscopy, you can see that little bit. And you can see the star doing away and towards us, away and towards. And that tells us about the mass of a planet and where it is. So this is the glorious story of spectroscopy until today. What do I do? And where do I come in? So I come in at the very closest inner regions of the protoplanetary disks that Andrea showed you. So Andrea takes images with ALMA of the global structure of the dust. I zoom into the innermost regions inside of, this is an artist illustration showing you a disk where there is a giant, there is a Jupiter mass planet that is carving a gap, and there is a residual disk here where rocky planets are forming. And with spectroscopy, different wavelengths, we zoom into these regions, not without getting an image. So we don't, again, I cannot show you an image, just an artist illustration. We get spectra, but those spectra give us the signal of hot gas that is in the star at these inner regions. So as you see in this composite slide that I use to present overall my work, I use spectroscopy at different wavelengths in the infrared, in the optic, the UV, and I also use millimeter interferometry connecting to what Andrea is doing to connect what the inner disk does in connection to what we see in the outer disk. And this is an ensemble of observatories that I've used using from the ground and from space. Some space telescope, the Spitzer Space Telescope, the very large telescope in Chile, Gemini telescope in Hawaii, IRTF in Hawaii, Keck in Hawaii, Elan in Chile, the VLA and ALMA, again, connecting to what Andrea showed you. In the UV, HST, the Hubble Space Telescope, and now finally, after waiting for many years, now finally James Webb, the James Webb Space Telescope. So when you observe spectra of protoplanetary disks where planets are forming, what can you see? The very first discovery that was made dates 2008. So it's a very recent research, because before 2008, we didn't have the good technology, good spectrographs enough to look at the planet-forming region in infrared spectra. So one of the earliest discoveries that really opened the field, I mean, as a young PhD student, is this one. It's shown here with a spectrum of a planet-forming region taken with Spitzer, the Spitzer Space Telescope, showing a forest of emissions from water. So all these lines that are not marked in any other way, these are water lines, and some simple organic molecules, acetylene, hydrogen, cyanide. No, they all have weird names, and carbon dioxide. This is more easier. And, so this was a big discovery. The message is we can observe water and organic molecules that are essential to build essential ingredients for life in regions where planets are forming. This made a big impact in the community. Now, so suddenly, from one day to the other, we realized that we have finally the instrumentation to detect molecules that are essential for life in places where planets are forming. So we can try to understand how those molecules incorporated into planets that may host life, may become habitable. So NASA, now given the great potential of this technique, NASA has been investing a lot on exoplanet missions in general, and in particular. So here is the Hubble Space Telescope, Spitzer that I already mentioned, and now we get to the time of the James Webb Space Telescope. So this one deserves a session and a little more focus that I'll dedicate in the last few slides. So the NASA James Webb Space Telescope was launched on Christmas Day. I don't know if you follow the launch. It was very much awaited after many years and problems and delays. It was finally launched on Christmas Day, not this one, but the previous one. So a little more than a year ago. Then it was in time what we call commissioning, meaning that the instruments on board of JWST that you see, they are here. Those instruments were being tested. So for 6 months until last summer, the instruments were being tested and just to whether everything was ready for science. And it is just since last summer, July, that science data started to be taken. And I was part of one of the teams who got some of the earliest data from the spectrographs on board on JWST. I will show. Just to show you here, to give you an idea of the monumental effort that this telescope took. Let me show you another image. This is an artist impression. This is an image of the mirror, of the gold-coated mirror as finished after finished assembling at the Goddard Space Flight Center. So you see here, they took the mirror, they took a picture where the mirror is reflection, NASA Goddard Space Flight Center. This was made on purpose by NASA. Here in this picture, you get an impression of the huge size of that. This is 6.5 meters. You see the engineers that were having it for a long time. And here you get in the artist impression, you see instead that the telescope is a very weird telescope. If you look at it, you probably wouldn't even immediately guess that it's a telescope. It's very unusual. And the reason of this shape is that you need a very large telescope that needs to be extremely cold in space. Space is cold, but not enough cold. If you place something irradiated by the sun, it will be warm. It will get warm. So what they built was you see 1, 2, 3, 4, 5, I think 5 or 6 layers of shields that are a little hard here to understand from this. They are a tennis court size. Okay, these are really big to shield this infrared telescope so that it's extremely cold. What has to be cold is the instruments. The instrument to observe in the infrared in order to be sensitive at these wavelengths in the infrared, so not where we see with our eyes, but in the infrared, the thermal emission that every warm body gives, even our bodies. So there you need to be extremely cold. That's why here, the oldest part of the telescope. And another thing that is worth seeing is the magic that was to send it into space. So now imagine that you have this telescope and you have to launch it and get it where it should go. So here, I love this image here. Again, it's not it's an artist illustration to show how the telescope had to be packed up and stored into the head of a rocket and launched into space. See? So this one became this one in space. So this was an extreme engineering effort. I would even call it art to be able to make something of this size and of this quality to fold into and fit into the head of a rocket. You see, so these are the shields packed up on each side. And this is the mirror. Even the mirror that you see is segmented. It's segmented for 2 reasons. One, because it's very difficult to build a large telescope, a large mirror. And second, because you had to fit it into the head of a rocket. So you had to close that telescope, that mirror, fold it, and then launch it, and then open it in space. So there were so many parts that NASA, even after a very successful launch, NASA was biting their nails for, I don't remember if it was 90 days that they were waiting to see that everything worked. And everything did at an amazing level, such that we have been getting amazing in this past summer. So just the last two slides. Now this is just one of the first spectra taken with one of these spectrographs on, and I was fortunate enough to be part of the team that got that spectrum. I have another program myself, actually, but given due to problems to the telescope, my program did not get data yet. So for the program that I proposed and I'm leading, but another program where I was supporting another team instead got their one spectrum. They proposed to get one object and they got it, and so they got to be the first. There is this beautiful spectrum from James Webb, and here is this team. Lindsay is a student of mine at Texas State, so she got to be on one of the earliest JWST papers. I'm very excited. She's a master student at Texas State University, and she worked with me for one semester. Okay, final view is JWST is also getting amazing data on exoplanetary atmospheres. Here, just one of the press release images, the official ones from the Space Telescope Science Institute, where you see, and I had to cut it into two slides, so this one and the next one, because it's so detailed. But so what you see here are unprecedented quality spectra of the thin layer of the atmosphere of a planet that is going around the star. So it's something that the technology has advanced so much that we can look at a planet passing in front of its star, and record the spectrum of the tiny atmosphere that is on that planet and study the chemistry and the potential for life of that planet. So this is one of the earliest examples. It's a gas giant, so we don't expect to see life there. But this is a demonstration of the quality of spectra from JWST. And you see here, there is water, monoxide, sulfur dioxide, carbon monoxide at different wavelengths. So these are spectra different wavelengths. And the next slide, again, water. So there is a lot of water detections. This is now clearly, you may imagine that water is one of the molecules that are most attention in exoplanetary science for habitability. And then sodium, carbon dioxide. So this is, I want to end not with a spectrum, but with a beautiful picture, just to say that we will see each other at the next discovery. This is one of the most beautiful images that was released with the James Webb Space Telescope of the cosmic cliffs. And just want to share as a final thank you and a final wish for all of us to go higher and higher in our discoveries.
Any question for Andrea?
Yeah, so in fact, water is surprisingly common in giant planets. So it was one of the earliest targets of Scorpio planets, again, for its appeal for habitability and its connection to habitability. I think JWST will now rewrite the census of molecules that we detect in other planets, and more importantly, will move down from giant planets to planets that we are even more interested in, which are those that are rocky and have an atmosphere on top of it. The super Earths that Andrea showed slides, those are like the big sisters of our Earth. So we are very interested in understanding their atmospheric composition. Now it's pushing truly the limits, even so we don't have an answer yet. We don't know, but in the giant planets, yes, water and carbon dioxide and carbon monoxide are common that are observed together also with sodium sometimes. Sodium here. You see? So it's still early times to really make a chemical census of exoplanetary atmospheres, but JWST is bringing us to a time when we can start putting together tables and answer your question.
Thank you.
Yes.
Have you discovered anything more complex than elements?
So, Andrea, if you can repeat the question, is it about the complexity of chemical elements?
So the question is, if there is life somewhere else, can we detect the spectroscopic signature of life, of complex organism?
Okay. And it's about life forms, especially, that you're asking about, or
Yeah. Any more complex life forms, if you will, than what you described?
Yeah. So, observing an exoplanetary atmosphere is the first step to have any chances to see any life signatures, because we expect that as on our Earth, the atmosphere of the planet should reflect a chemistry that is disturbed by life, or that is no. So the question of whether planets, in science we say habitable astronomy, we call habitable planets, but we still simplify what that means. Habitable for us simply means that it's at the right distance from its own star to have liquid water on its surface. But it doesn't mean that it has it, and it doesn't mean that there is life there. So to really be claim that we detect a life signature, we really have to observe the exoplanetary atmosphere, which is again what was telling us to do and Hubble before, and it's really the first step. Now, from there to knowing whether we have detected a life signature is a very complex chemistry question. Because again, think about it, you observe an atmosphere and you want to see a sign of some sort of disequilibrium in the chemistry that cannot be attributed simply to natural phenomena that do not include life. And I on that field, I follow what my colleagues do, and so it's about biochemistry, biology, chemistry, astrochemistry, and it's a connection of fields where they try to answer this question: what is the one thing that will tell us that there is a form of life on another planet? And so far, it's not clear. It's a very complex question, but there are some chemical disequilibrium signatures that can be extracted from these observations, actually will bring us to determine whether, again, that signature is can be attributed to life or not.
Looks like we don't have any more questions, so I think we can let you go, Andrea.
Thank you very much again.
Thank you.
It's always a very great pleasure to be where like young Italian scientists like give us presentation so fascinating, I have to say. It's always make me feel like very proud. So many compliments and thank you for participating tonight with us and to share with us like your work, and that is really interesting and fascinating, I have to say. We have just a little, something to remember tonight, and to thank you for your participation. Just to put in context a little bit this initiative and this project that I really like, and I hope like they can grow more. Is the objective is to be together with Italian scientists. There are many of them active in Texas and also in the other states that are part of our area of competence, and also to facilitate a networking among Italian scientists and to facilitate the contact with the Consulate as well, because Italian scientists that are operating in Texas and the other states are seen from Italian institutions as a very important asset to achieve the object of our scientific policy here, that is like to strengthen the relation between the Italian science and research compartment and the American one. So you are like our main asset to that. And so it's very important. Your work is very important for Italy. Thank you.
Thank you.